Hello, today we're going to start section 11.2, which is called Inference for Relationships. Basically, what we're going to be doing in this section is looking at two other types of chi-squared tests. If you think back to chapter 10, we learned two sample Z procedures to compare the proportions of successes in two populations or for two treatments in an experiment. But what if we wanted to compare more than two samples or groups, like 3 or 4? How do we do that? And what if we wanted to compare the distributions of a single categorical variable across several populations or treatments? Well, for those types of questions, we need a new statistical test. And the way we start that test is we look at a two-way table. So we looked at two-way tables a while back. They have more general uses than comparing distributions of a single categorical variable. They can be used to describe relationships between two categorical variables. So we're going to start by looking at a test to determine whether the distribution of a categorical variable is the same for each of several populations or treatments. And later in this section, we'll be looking at a related test to see whether there is an association between the row and column variables in a two-way table. So these are going to be the two other types of chi-squared tests that we're going to learn in this chapter. All right. So let's say market researchers suspect that background music may affect the mood and buying behavior of customers. So there was a study in a supermarket that compared 3 randomly assigned treatments. They had no music playing, they had French accordion music playing, and they had Italian string music. Now, under each of these conditions, the researchers recorded the number of bottles of French wine, Italian wine, or other wine was purchased. And then here's a table that summarizes the data. So for example, when no music was being played, they sold 30 bottles of French wine, 11 bottles of Italian, and 43 bottles of other wine for a total of 84 bottles, and so on. So here's what we're going to try to answer. We're going to start by calculating the conditional distribution in proportions of the type of wine sold for each treatment. And then we're going to make an appropriate graph for comparing the conditional distributions in part A. And then we're going to try to answer, are the distributions of wine purchases under the 3 music treatments similar or are they different? And we're going to give some evidence to support that. So if you remember what a conditional distribution is, and this was a while ago that we first learned these, a conditional distribution basically takes both variables into account. So basically, when no music was being played, what percent of the wine we sold was French, what percent was Italian, and what percent was other. So basically, we just take that number and divide it by that number, and then take that number divided by that number, and then take that number and divide it by that number. Okay, so when no music was being played, here are the proportions of each type of wine that we get. And then the conditional distribution, we're going to figure out for all 3 types of music. We do that number divided by that, and then 1 divided by 75, and then 35 divided by 75. So when French music was being played, that's the proportion of each type of wine that was sold. And then when Italian music was being played, that divided by that divided by that, and that divided by that. And those are the proportions of types of wine when Italian string music was being played. So that this right here, all 9 of these proportions would be the conditional distribution for each type of music. Now, how should we display this information in a graph? So since this is categorical data, that definitely limits our choices. Basically, it's bar graphs or circle graphs, and we could do circle graphs because they do add up to 100%, but I'm going to use bar graphs here. I'm going to make separate bar graphs for each type of music, and my bar graphs will look like this. So you can see then in part C it was a question of, are these distributions very different or are they similar? So in what ways are they similar and what ways are they different? One big difference you can see here is the amount of Italian wine changes a lot between these three different types of music. So you can see very little Italian wine when French music was being played, around a little more than 10%, close to 15% when no music was played, and over 20% when Italian music was played. So you can see the type of wine the customer buys seems to differ considerably across the three types of music. Sales of Italian wine are very low when French music is played, higher when Italian music or no music. Now, French wine appears to be pretty popular in this market, selling well, doing a pretty good job under all three conditions, but notably better when French music is being played. And then the other types of wine are, fairly close in all three treatments. So we are going to look at a way to do a more complex analysis of comparing these three to each other. Because basically the question we're going to try to ask is like, are these really that different or not? We're going to try to like measure how different they are from each other. Basically the question is like, these are all three different like samples, let's imagine, from some, population. Now, could the population that each one of these three samples came from, could the populations be the same, is one way to think about this. So like if you think about averaging these three different distributions, could it be possible that all three of these came from that like average distribution? Well, it could be, it's always possible because, we can get, variation when we take random samples, but that's what we're going to try to measure is how likely is it that we could get distributions that are this different, even though the, populations they would come from are the same. So one of the problems here is we're trying to do a lot of comparisons at once. I'm trying to compare, French wine in three different treatments, Italian wine in three different treatments, and the other wine in three different treatments. So that's like 9 things I'm trying to compare all at the same time, which is a lot more than we've done when we did, a 2-sample t-test. That's only comparing 2 things at a time. So this is the problem of multiple comparisons. In order to handle that, we usually have 2 parts when dealing with multiple comparisons. So we use an overall test to see if there's good evidence of any differences in the parameters that we're trying to compare. And then we do a detailed follow-up analysis, which we talked about in section 11.1 as well. Now, the overall test that we use here, we're going to use that familiar chi-squared statistic and distribution that we learned in 11.1. So we're going to talk about, just step 1 here of the overall test. To perform this test, we're going to use hypotheses and this null hypothesis and this alternative. So the null hypothesis is that there is no difference in the distribution of a categorical variable for several populations or treatments. Okay, and then the alternative is that there is a difference in the distribution of a categorical for several populations or treatments. So the null hypothesis would be that these, 3 distributions are actually coming from, 3 distributions that are the same. Okay, the alternative is that, the populations these come from are actually not the same. And then what we do is we compare the observed counts in a 2-way table with the counts we would expect if the null hypothesis were true. So just like 11.1, we compare the observed counts to the expected counts. So for these, though, how do we find the expected counts? So if you think about going back to this table here, like what should we expect to get right here then? Now, one of the key differences here in 11.2 is I don't have some preconceived percentage that I am, using as my null hypothesis for each type of wine. Instead, I'm saying that this, arrangement is the same as this, is the same as this, is the null hypothesis. So how do we find the expected counts? Well, here's what we do. So the null hypothesis is that there's no difference in the distribution. So our null hypothesis is that the type of thing being played didn't make a difference. So to find the expected counts, we assume the null hypothesis is true. So what that leads us to do then is it leads us to look at this column right here at the end, this total. So like this is how many French bottles total I sold during all 3 treatments. So my assumption is going to be that 99 out of 243 is the percent of French wine that I sold in total, which means my null hypothesis would be that that's the percent of French wine that I sell no matter what is being played. So basically, if I do 99 divided by 243, I get that it's almost 41%, 40.7%. So basically, using the null hypothesis, I would assume that I'm going to sell this percent of French wine no matter what, under any treatment. So basically what I do then is I say, okay, well, when there was no music, I sold this much wine. So my expected count would be that that percent of this is going to be how much French wine that I sold. So it's going to be like 99 out of 243, that's the percent of French wine I'm going to sell of this total. So I'm still going to assume that that total amount of wine I sold is 84, and that will give me an expected count right there. So when I do that calculation, you can see here I get 34.22. And then again, when French music is being played, I expect to sell this percent of wine. So I expect to sell this amount of French wine no matter what music's played. So I do that percent of this total to get this expected value, and then I do that percent of this total to get this expected value. So I use that same fraction here times each of those totals to get these expected counts right there. And then I do the same thing for Italian wine. So overall, there were 31 total bottles of Italian wine sold. Out of the total number of bottles means I expect to sell about, 12.8% of the wine I sell should be Italian, no matter what music's being played. So I do that fraction times the total 84, that fraction times the total 75, and that fraction times the total 84 to get these 3 expected counts. And then I do the same thing for Italian wine. I expect to sell, other wine I expect to sell, about 46.5%. So I do that fraction times that total to get that expected count, and so on for those. And then those are all 9 of my expected counts. Okay, so let's look at figuring out this expected count right here. I did 99 out of 243 times 84. So if you can see, this is the calculation I used to get this number, and these are the 3 numbers that I used. And then what I can do is I can actually rearrange that calculation, and instead I could do this times this divided by this, and I'll get the same answer. And the reason I do that is because then we've got a nicer formula here to figure out expected counts. So the formula to figure out the expected count in any cell is given by the following. You do the row total times the column total divided by the table total. So if I want to figure out this expected count right here, I do the row total, which is right there, times the column total, which is right there, divided by the table total. And that's going to be my formula to figure out any expected count in any two-way table. So you can see if I wanted to figure out like this expected count right here, I would do the row total times the column total divided by the table total. So that's going to be the formula you can use to figure out your expected counts. So I think that's where we'll end there today. And then during our next lesson, we'll talk about checking conditions and actually then calculating the chi-squared statistic for a situation like this.